So it's truly a pleasure and honor to be in such distinguished company. And I have, I think, an interesting story to tell you. But first, imagine what it was like 120 years ago when X-rays were first developed and physicians could look inside their patients' bodies. They could see whether a bone was broken, a tendon was torn, maybe a tumor was growing. They could see inside. They could see what was happening. And what I'm going to tell you about today concerns the ability to see inside the brain, but not the tissues. I mean, we can see the tissues, and as I said, we've been able to for 120 years. But what happened, there's a development of a new technology, MRI. Many of you have seen MRI machines, maybe been in one, or you know someone who's been in one. And 25 years ago, scientists found a way to use MRI machines to see not just the tissues, but to see the activity of the brain. And you've probably seen in various newspaper articles, magazines, pictures of the brain with hot spots in it. And that's what fMRI, functional MRI, the brain function being measured, did initially, measured the hot spots where the activation was. And that was useful, and some special populations had differences, some areas didn't activate, and so on, or overactivated. But the brain isn't just for hotspots. The brain is essentially an information processor. And so my colleagues and I asked, could we find out what information is being processed in those hotspots? Could we find what thoughts were going on in a person's brain? So first of all, just a little exercise. I'd like you to think about an apple. Think about what an apple is. So simple enough. And so my next slide says, and it's kind of true, if you're in an MRI machine, I can tell what you're thinking. I could have told that you were thinking of an apple at that moment. It's because each concept has a brain signature that can be read out in an MRI scanner. And I'll tell you a little bit about that story. In one of our first studies, my colleague, particularly Tom Mitchell and I, who was a machine learning scientist, we gave people 60 items to think about, one at a time. Apple was one of them, I believe. And we just have someone in an MRI scanner. There's a screen inside. They can see the screen. Some word comes up, and the person is instructed to think of the concept that the word refers to. And so we do this, and I'll briefly tell you what we measure. We electronically dice up the brain into 20,000 volume elements called voxels. Actually, we only really need to pay attention to about 200 of them that are really players in representing concepts. And the neural signature of a concept is the activation level of each of those 200 voxels measured with fMRI. So the activation level is what the machine measures, and it's a measure of how much electrical activity is going on in each little volume element. Each volume element is maybe 100,000 or 200,000 neurons. But together, that pattern of activation is the signature of a concept. We're able with this program, and it's not a human being. It's not me or a research assistant decoding it. We give this to a machine learning program. We train the program, say, 2/3 of a person's data, and then we give it data that it hasn't seen before, activation patterns, and we say, what is this? And it says apple or hammer or whatever. And it does very well. It gets 72 or 84% correct of the concepts. It's far above chance level. And I should tell you, we need extreme cooperation from people. We could never do this against a person's will. We need them to lie very still. We need them to concentrate on the concept and so on. So you needn't worry that people are going to read your mind against your will. So here's the second idea. And I find this one of the most amazing things about our research. Everybody's brain represents a given concept approximately the same way. An apple is an apple. 3 minutes ago when I asked you to think about an apple, the amazing thing is there was a very similar activation pattern in each of your brains. I find that amazing. You know, we think of ourselves as unique human beings. You know, I've had this experience with Macintosh apples and I love them and so on and so forth. And there is individuality, of course. But under the skin, there's a tremendous amount of commonality in the way we represent these concrete objects. And it's not just concrete objects. To be more precise, we trained the program on the activation patterns of 10 people. We tested on the 11th person, and it's just as accurate as if we trained it on the person's own data. It means that it works across people who speak different languages, even monolingual subjects. We tested people who were monolingual Portuguese. And an apple is the same as pomme, is the same as manzana. It's the concept. And it's due to the universality of our brain biology. All our brains are built the same way. And to some extent, our experiences is all the same way. We all live in a gravity field. We have a horizontal plane we walk on. The sun rises in the morning and so on. And together, that creates a system that's common. And it's the patterns, I told you that we have neural signatures. These signatures aren't arbitrary patterns. It's not just a mess of 200 voxels doing whatever they want. They're very systematic. They represent elements of meaning. They have structure. For example, for the concrete objects, there are 3 main dimensions of representation. One of them, one part of the dimension of representation is how your body interacts with the object. For example, if you were to think of a soccer ball, part of your representation of a soccer ball will involve the representation of your leg kicking it. If you're thinking about a pair of pliers, part of the representation of the pliers will be your hand clenching them. For other objects, such as house, there's a part of your brain that encodes shelter or enclosure. It'll activate those voxels, and they're not all in the same place. Will activate for house, for umbrella, for closet, for car, because you have enclosure. And a third dimension that emerges has to do with whether it's eating related or not. So our brains are using these dimensions for organizing information about concrete objects. It's part of the brain's indexing system. It's just when you go to file something away in your own indexing system, you have some organizational structure. And here we're starting to uncover the brain's organizational system. And we can use this, it's precise enough that we can predict the activation level of a new object. So we had 60. Here's an example for apartment. For the computer program can now predict the activation pattern for a new image that it hasn't seen before if it knows what kind of object it is. So if you have a favorite object, whether it's kumquat or violin or whatever, to first order, I can predict using this model what the activation pattern will be. So there's some common underlying dimensions of brain representation. An apple is how you hold it, how you taste it, and so on. So I'm going to show you a brief video here.
Neuroscience research into how we think and what we're thinking is advancing at a stunning rate, making it possible for the first time in human history to peer directly into the brain to read out the physical makeup of our thoughts. Some would say to read our minds. Whatever you want to call it, what neuroscientist Marcel Just and his colleague Tom Mitchell at Carnegie Mellon University have done is combine fMRI's ability to look at the brain in action. Think about a screwdriver, and the computer found the place in the brain where that person was thinking screwdriver?
Screwdriver isn't one place in the brain, it's many places in the brain. When you think of a screwdriver, you think about how you hold it, how you twist it, what it looks like, what you use it for.
And each of those functions are in different places?
Correct. And we found that we could identify which object they were thinking about from their brain activation patterns.
You're reading their mind.
We're identifying the thought that's occurring.
Inside the scanner, Megan was shown a series of 10 items and asked to think for a few seconds about each one. Within minutes, the computer, unaware of what pictures Megan had been shown, and working only from her brain activity patterns as read out by the scanner, was ready to tell us, in its own voice, what it believed was the first object Megan had been thinking about.
I think the word is knife.
All right, one.
Bingo. All right. Then the second.
I think the word is hammer.
All right.
I think the word is window.
It's perfect, right?
So far.
And it continued to be, word after word.
Apartment.
10 out of 10.
10 out of 10. Well done, well done.
So the woman in red is Megan. She was the associate producer. She went in the scanner. The program had been trained on the data of other people, and it could tell what she was thinking. So concrete objects it's cool to be able to do that, but there's other aspects of human thought, for example, emotions. With some colleagues, we had people evoke emotions in themselves: anger, disgust, and envy. You can see the list there: pride, sadness, shame. And we could act very accurately to tell which emotion a person was feeling. And again, somewhat surprisingly to me, there was a commonality, a very high degree commonality across people. So when I feel anger, I feel that it's very personal, that nobody else could possibly know what it feels like to me, and yet the activation pattern is almost the same across all of us. Anger is anger. I want to mention, what are the underlying dimensions here? It's not eating and object-body interaction. The dimensions are intensity, the difference between being furious and being annoyed. Valence, whether it's something positive like happiness or something negative like sadness or loneliness. And a social factor, whether there's a second person involved. For envy, you need another person. For sadness, you could be sad all by yourself. So you see three more kinds of indices with which the brain organizes these, I'm not sure we'd call them thoughts, but mental states having to do with emotion. And it's not just emotions, it also works for procedures, not just knowing that, but knowing how. We taught people how to tie 7 different knots, and if you do any sailing, you know that there are different knots for different purposes. You know how to quickly tie one. Well, we taught our participants to tie them. We put them in the scanner, and we say, imagine tying a sheet bend knot. And as they mentally tie it, we get their mental representation. Now this is distributed, unlike the apple, this is distributed over time. It's a sequence of states, and the program learned the sequence of states and could identify which knot was being tied, again, very accurately, with possible applications to the learning of medical procedures, mechanical procedures, computer user procedures. We can tell how well somebody represents something, and we could tell which of various procedures they're thinking about. So another brief video.
Do you think one day, who knows how far into the future, there'll be a machine that'll be able to read very complex thought, like, I hate so-and-so, or, I love the ballet because.
Definitely. And not in 20 years. I think in 3-5 years. Ample does.
3 years.
Well, 5.
So Leslie Stahl, that was an unexpected question. I didn't know she was going to ask me that. She asked me that question in 2008. And I want to show you the results of a study that we did in 2013. It was published, I think, in 2016 or 17. And she was saying, can you possibly decode complex thoughts? I'm not that interested in apples and hammers. I want to know, I hate so-and-so. So here are the actual combinations of concepts that we tested. Instead of I hate so-and-so, we had the old man threw the stone into the lake, the commander listened to the soldier, the happy child found the dime. So most of our thoughts are multi-concept thoughts. We don't just simply, most of the time, think of a chair. We think about combinations. And so we found a way, it involved a slightly different method. We found a way of identifying complex, multi-concept propositions or sentences. So we were able to do it, and we did it in the 5 years. Again, it's not just getting the pattern, but knowing what the pattern consists of, being able to predict the pattern. If you look at this slide, you see, amazingly, we can really predict the activation for a complex thought, like the minister spoke to the injured patient. I should say, the program doesn't get down to this level of detail. It knows that there's a communication between people. It knows possibly that there's sort of some spirituality involved, and it possibly knows something medical is involved. So it doesn't really know the sentence. It knows the semantic elements of the sentence. And you could say you could rightfully say this is very cool, but who cares? And the reason we care is because you understand how something works, you can do magic with it. You can make it work better, you can repair it when it breaks, rather than just hoping that it does its job. So one of our studies had to do with physics concepts, and unlike apples and hammers, concepts like centripetal force and displacement and electric charge, they're much more abstract. You don't see it all the time, you can't hold it with your hand most of the time, yet we ask, can we possibly decode this? We do this with physics students, and again, the result is we can decode the individual concepts. There's commonality across people. Everybody, doesn't matter where they got their training, represents these concepts the same way, even though they're abstract concepts that have been invented only in the past 300-400 years. So I want to show you the interesting underlying factors. Now, it's not eating or holding or an intensity of an emotion. The kinds of underlying dimensions for these physics concepts are more everyday things like visual motion, visualization, imagining something hitting something else and causing it to move. Periodicity, something periodic. Think about how when the drum band was on the stage, think about how that affected you. Maybe your toes were tapping, but it was very stirring, and you could ask why. I think because there's a brain system that processes rhythm. It responds to a drum band. It also responds to the sound of persons saying the sequential words of a sentence, something that a baby learns as they're learning language. And when the physics professor says, today we're going to talk about sine waves or frequency or light waves, that same brain area activates. So these underlying dimensions of representation emerge from the kinds of things that the brain has developed, that biology, Mother Nature, has given us over millennia to deal with the world. I'm briefly finally going to get to suicidal ideation. Psychiatric illnesses are thought disorders, and if that's the case, if we can measure thoughts, maybe we could measure disorder in thoughts. We trained the classifier, the program, to distinguish young people, 18 to 30 years old, those who have been thinking about suicide versus healthy controls. And we give them words like death, trouble, and good. And the program is fantastically accurate. With 91% accuracy, we can tell who has been, who hasn't been thinking about it. Some of the most discriminated concepts are death, cruelty, trouble, and so on. But this approach tells you not only that death is different, it tells you how it's different. People who are thinking about suicide, for death, it evokes more shame and, geez, I've forgotten the other difference. Oh, yes, and it's associated with the self. The self and shame among the ideators and not so among healthy controls. Also, the program can tell the difference between those who have made an attempt and those who haven't. Also works with autism. Well, so now I'm running low on time. So here's the seventh idea. The other ones I know are true because we've done it. But the seventh one is more speculative, and that's that learning precisely how our brains work will enable the next major leap in human intelligence and mental health. Several of the speakers have talked about how, we're getting smarter over the years. We have educational institutions, we have better nutrition, we have better medical care, and I think understanding brain function will be another big leap in human intelligence. And intelligence, as I think 3 of the other speakers have told you, intelligence is adaptive thought, being able to think with fluid intelligence, with creativity, and so on. And we're going to be able to think in ways that our ancestors weren't able to. Our progeny will be better thinkers than we are, enabling them to further advance civilization. Thank you.